All right, so again, test 2 is about probability and probability distributions. So we talked about probability in general on chapter 3, and then now we're going to talk about probability distributions for chapter 4. So we always start off with like the boring vocabulary, so let's get it over with. The probability distribution function for a discrete random variable. Remember that discrete means countable. Whenever we're talking about a random variable, it describes the outcomes of a statistical experiment in sentence form. It's usually represented by capital X, and a specific outcome is represented by that specific X. So there's 2 types of random variables, just like we talked about before, discrete and continuous. Discrete assumes countable values, so stuff that we can count on our fingers. Some examples that I took straight from the homework are the number of runs by a softball team. So the number of runs by a softball team each game. Or another one that was on the homework was the number of hurricanes that made landfall each year. So these are discrete because we can count them. And they're also a variable because they can change. Every year it's going to be a different number of hurricanes. Every game is going to be a different number of runs. Whereas the continuous, like we talked about before, assumes any value contained in 1 or more intervals. So some examples straight from the homework was the speed of an airplane. A commute distance. And amount of electricity. So these are all items that are over an interval. So it doesn't have to be a whole number. It could be decimals. They're also measurable. So let's put that here, measurable. Distance, time, money amount, that type of thing. So a probability distribution is a table that lists or shows all possible values that a random variable X can assume and their possible probabilities. So instead of just saying the probability of pulling out a red marble out of a bag, that's just one specific thing. This gives us all the different options and then the probability for each option. So properties of a discrete probability distribution, just like we talked about before for probabilities in general, the probability of a variable X must equal or lie between 0 and 1. 0 means it's definitely not going to happen. 1 means it's 100% for sure going to happen. Any decimal between there. Just like we talked about before for probabilities, the sum of probabilities in a valid probability distribution must equal 1. Remember that we use those symbols for that. So our capital sigma, which is kind of like our weird looking E, which means the sum of the probability. So the sum of P of X is going to equal 1. That's just our way of saying the sum of the probabilities is going to be 1. That's our way of writing that sentence as a symbol. And then lastly, probabilities are always approximate. They are never exact. So straight from the homework, it gave us some probability distribution tables, and it says, are these valid or not? Like, do these make sense to be a probability? Do they follow these properties or not? So our answer is going to be yes or no. So our first one says that X is going to be 1, 3, 2, or 0. And here's our probabilities. So we're looking, are these probabilities between 0 and 1? We have 0.01, 0.51, 0.42, and 0.06. But yeah, they're all between 0 and 1, so that's good. And whenever we add them up, I know 0.01 plus 0.51 plus 0.42 plus 0.06. Our sum is 1. So the sum of the probabilities does equal 1. So it satisfies those conditions. So our answer is yes. It represents a valid, that's not high school valid, probability distribution. So I'm just going to make a note just so I have to write it every time. So what this is saying is we're going to try to see if the probability, so P of X, satisfy the conditions above. We're trying to see if P of X satisfies the condition above. Notice I say that see if P of X satisfies. These are probabilities. I don't care what X is. X is just my different options. So I'm not even really looking at my X column. So I don't care about X. Or these are just your notes. So write whatever. I know I don't use proper grammar, but use whatever will help you. But I don't care about X. Those are just my different options that I have to choose from. I'm trying to see, do these probabilities work? So let's go on to the next one. So here's my different options for X, 4, 5, 6, 7, 8. Here are my probabilities. So 0.28, 0.17, 0.17, 0.06, and 0.37. So they're all between 0 and 1, so that's good. And let's see, whenever I add them up, does it equal 1? So 0.28 plus 0.17 plus 0.17 plus 0.06 plus 0.37. It doesn't equal 1. So the sum of our probabilities does not equal 1. So no, it does not represent a valid probability distribution. Same thing down here. My X values are -1, 5, 6, 8, 2, 1. That's fine. I don't care what these are. My probabilities are 0.2143, 0.1607, 0.3393, 0.1071, and 0.1786. Those are all between 0 and 1, so that's good. So let's see if I add them all up. I do get 1, so that one's good. So all my probabilities are between 0 and 1, and the sum of adding up all the probabilities does equal 1. So yes, it represents valid probability distribution. So that one's good. My last one, my X values are 1, 2, 3, 4, 5, 6, 7, which is fine. I don't care what it is. My P values are 0, 0, negative 0.438, 0.313, 0.750, 0.445, and 0. Well, just by looking at it, I have a negative. Not between 0 and 1. Or in other words, cannot be negative. Whatever you understand better. So our answer is no. It does not represent a valid probability distribution. And that's it. If that was the whole test, it'd be good. Questions, comments, concerns from you? Are you guys okay? You guys seem like quieter today, which is fine, but I was just checking on you. Yeah. Okay. A few more seconds on here. I'll go to the next page. All right, page 2. Translate the following statements into probability notation, just like function notation, where we could say the probability of whatever our scenario is. Just like function notation, like we say f of x, this is the probability of whatever. So use x as the random variable. So it says the probability of x being no more than a. And I try to put, like, I went through all the different homework scenarios because these wordy things get people. So I try to put down all of them that I've seen. So the probability of x being no more than a. So no more than, that's like the weird thing here. So the probability that x is no more than. So no more than means it's going to be less than or equals to a. It could be a or anything less. So probability that x has to be less than or equal to a. We're going to use this a lot. So the wordy stuff, refer back to this example because this wordy stuff gets people. And we're going to go from the sentence form, and then we're going to go to the symbol form or whatever. So the probability of x being at least a. So now we're looking at the words at least. So the probability that x is at least a. So it could be a or anything bigger. So greater than or equal to a. Could be a or anything bigger. So the probability that x is greater than or equal to a. I don't like these squiggly things, I might just underline it. So the probability of x being at most a. So the probability of x being at most. So that means it could be a or anything less than that. So less than or equal to a. At most. So it can't be anything more than a. So probability of a is being less than or equal to a. The probability of x being no less than a. So no less than. So the probability of x being no less than a. So a or anything bigger. So greater than or equals to. The probability of x being greater than or equals to a. The probability of x being more than a. So notice it just says more than. So the probability of x has to be greater than a. It has to be more than a. It can't equal a, it has to be more than that. So the probability of x is greater than a. Last but not least, the probability of x being exactly a. So the probability of x equaling a. So I know from talking to you guys and from doing this class so many semesters, that the wordiness gets people. So this is where I wanted to make sure that at least you have an example of all the different weird ways of wording it. So questions, comments, concerns on these before moving forward? How could I help make these better? All right, so let's not all talk at once. Next example. So the local bakery has determined a probability distribution for the number of cheesecakes that they sell in a given day. Let X equal the number of cheesecakes sold in a randomly selected day. So that means 0 cheesecakes, the probability is 0.22. If we have 5 cheesecakes, that means that it's going to be 0.07. If 10 cheesecakes were sold, that means it was going to be 0.29. We don't know about 15, and then 20 we know is going to be 0.09. So using this table, I'm going to scroll up a little bit. Using this table, part A says, what's the probability of selling 15 cheesecakes in a given day? So the probability, putting this just like we did from up here, of being exactly 15. So the probability of X equaling 15. We don't know. They didn't tell us that. But I do know that all of my different probabilities, if I add them all up, the sum of my probabilities is equal to what? 1. So that means if I do 1 minus all of this stuff, so 0.22 plus 0.07 plus 0.29 plus 0.09, that should be my answer. Or if you want to say plug in X and then solve for X, you get the same thing. So I know 1 minus, make sure you put in parentheses, 0.22 plus 0.07 plus 0.29 plus 0.09. That will tell us what's left over, and it's 0.33. So we know for 15 cheesecakes, our probability is going to be 0.33. Next says, what's the probability of selling at least 10 cheesecakes? And this is kind of nice because it gives you the symbol version. So it says, what's the probability of X being greater than or equal to 10? So that means it's equal to 10 and then everything bigger. So the probability that X is 10 plus the probability that X is 15 plus the probability that X is 20. Now, on your notes, do you have to write this? No, I'm just doing it so that way whenever you go home and you look at your notes, you realize where we got these numbers from. So 10, because it says or equals to 10, and everything bigger. So the probability that when X is 10 is going to be 0.29, plus when X is 15 is 0.33, plus when X is 20 is 0.09. So we're just going to add all those different probabilities together to give us the total probability. So 0.29 plus 0.33 plus 0.09, which will give us 0.71. So just adding up those different probabilities. Next, it says, what is the probability of selling 5 or 15 cheesecakes? So that or means we can also add. So probability of 5 plus the probability that X equals 15. So for 5 cheesecakes, we know that's 0.07. Plus 15 cheesecakes, we know that's 0.33. So adding those together, we get 0.4. I'm going to put it up here. So the next one says, what's the probability of selling 25 cheesecakes? Remember, probability distribution gives us all of our options. 25 is not an option. So what's the probability of selling 25 cheesecakes? 0. There is none. No. So there is no possibility. So 0. Thank you. So from our table, we know it cannot be more than 20. Or not an option. Not an option. So just 0. Last one, what's the probability of selling at most 10 cheesecakes? And again, it tells you in symbol form the probability that x being less than or equal to 10. So less than or equal to 10. So probability that x is 0 plus the probability that x is 5 plus the probability that x is 10 because or equals 2. For 0, our probability is 0.22. Plus for 5, our probability is 0.07. Plus for 10, our probability is 0.29. So just adding those all together will give us 0.58. 0.58. And that's it. Maybe I'm nerdy. Oh, I know I'm nerdy, but I like these. It's kind of straightforward. But before we go to the next page, questions, comments, concerns, how can I help make this easier for you, please? All right, if not, let's just keep rolling. So next page. So Andrew finds that on his way to work, his wait time for the bus is roughly uniformly distributed. Uniformly distributed means it's about the same. So between 13 and 24 minutes. One day, he times his waits and writes down the number of minutes, ignoring the seconds, and rounds to the 3 decimal places if needed. So here's our little chart or whatever. So this is the wait time measured in units rounded, and then there's the probability. So what is the probability that Andrew waits for 14 minutes? So because they are all about the same, notice we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 options. We have 11 options. So what's the probability that x is 11? Oh, I don't know where I'm getting 11. 14. There's one option out of the total 11 because they're all the same. So it doesn't matter where they land. It's all the same. So one divided by 11 would give us 0.090909 blah blah blah. It tells us to round to 3 decimal places. So looking at the third number after the decimal. So 1, 2, 3, looking at this 0. Looking next door is a 9. It's 5 or higher, it rounds up. So that 0 is going to round up to about 0.091. 0.091. So because they're all the same, we can just use it as regular probability. There's one option out of 11 options total. Kind of weird. So that's why I wanted to go over it together. But now that you see it, hopefully it will be easier. Same thing for the next one. What's the probability that Andrew waits between 18 and 23 minutes? It gives it to us in symbol form. So probability that 18 is less than or equal to x is less than 23. So remember that less than or equals to means that 18 is included. So we have 18, 19, 20, 21, 22, but it says just less than 23, so 23 is not included. So we're just looking at 18, 19, 20, 21, 22. So that's 1, 2, 3, 4, 5 options out of our total 11. So my calculator, 5 out of that total 11 would give us 0.45, 45, 45, blah, blah, blah. Again, rounding to 3 decimal places because the problem told me to do so. I'm looking for the third number after the decimal. So 1, 2, 3, looking at this 4. If I look next door, we have 5. 5 or higher rounds up. So that means our answer is going to round to 0.455. 0.455. And that's it. We have one more for this page. Before we go there, how can I help make this one easier for you? All right, fine. The following table gives the frequencies of the nest size, which is the number of eggs of 134 great blue heron nests recorded on a recent survey in Indian River County. Use the data to construct a discrete probability distribution. So it gives us the data, it asks us to find the probabilities, which is fine, we can do it. So this is the number of eggs, so and the frequencies. Remember, F means the frequency. So the number of nests with 0 eggs, there's 1 of them. There's 47 nests with 1 egg. There's 25 nests with 2 eggs. There's 12 nests with 3 eggs. There's 35 nests with 4 eggs. And there's 14 nests with 5 eggs. So that's how we would kind of read that. So we know total too, there's 134. And if you add it up together, that would give you that 134. 1 plus 47 plus 25 plus 12 plus 35 plus 14. We'll give you that 134. So total, we have 134 nests. So construct the probability distribution of X, where X is the number of eggs in a randomly selected great heron nest in Indian River County, round to 3 decimal places as needed. So what's the probability of having 0 eggs? So we know there's 1 of those out of our total 134. So 1 out of our 134 would give us 0.007, rounding to 3 decimal places. There's 47 nests with 1 egg. So 47 out of our total 134 would give us 0.3507. So that'll round up to 0.351. With 2 eggs, we know there's 25 nests out of our total 134. So 25 out of our 134 would give us 0.1865. So that 65 is going to round up to 7. 0.187. There's 12 nests with 3 eggs. So 12 out of our total 134 would give us 0.0895. So that 89 is going to round up to 90. So 0.0895, blah, blah, blah. We're rounding this 9, looking next door is a 5. So that 89 is going to round up to 90. Make sure to put that 0 at the end though, because that shows that you rounded to 3 decimal places. Don't leave it as 0.09. Or else it'll think that you only rounded to 2 decimal places. So for 4, we have 35 eggs, or 35 nests with 4 eggs. So 35 out of 134 will give us 0.261. And last but not least, 5 eggs, there's 14 nests, so 14 out of our 134 which is 0.104. And that's it. So we just found the probability like we did in chapter 3, but just found the probability for each of them separately. So that's our probability distribution. It gives us all different options in one table. So now I can construct a probability distribution graph for this nest size of the great blue herons in Indian River County. So it gives me like the setup. Remember that on the homework on the test, it's going to be multiple choice. Here's our nest size and here's our probabilities. So for 0, our probability is 0.007, so something like really low. Remember, by the way, that this is quantitative data. So we're going to use a histogram. Does it matter? No, because your options are all going to be histograms. But I just want to kind of throw that out there. Remember, a histogram is a bar graph with all your bars touching. So for 1, we have 0.351. So somewhere between 2 and 4. For 2, we have 0.187, so almost a 2. Almost a 0.2. For 3, we have 0.90. So about halfway up between 0 and 0.2. For 4, we have 0.261. So just above 0.2. And last but not least, for 5, we have 0.104. So in between 0.1 and 0.2. That's it. So another question that they might ask on there is, what's the shape? So it's our options, remember, are uniform, so they're all the same. It's not uniform. It could be left skewed, right skewed, where it has like the hump and then the tail, or it could be random. Here, there's no hump and tail. It's all just kind of like goes up and down, so that means it's going to be random. So a random histogram. A random histogram. And that's all of page 3. Questions, comments, concerns? How can I help you with page 3? All right, let's do one more page and then we'll take a quick break because we'll be halfway through. So one more page, page 4. And then we'll take a quick break and then we'll wrap it up. So formulas for discrete random variables. So our mean, which is also called our expected value, they're synonyms, we use the same, use it interchangeably, is mu. Remember, this is our symbol mu, like we talked about before. E of x, which is for our expected value. And it's going to be the sum of x times p of x. So adding up our x's times our p of x. And it's the long-term average, or what is expected over many experiments. So our variance, we use sigma squared, which is the sum of adding up x squared times p of x minus our mu squared. And our standard deviation is just the square root of our variance. So it's just sigma, it's the square root of our variance, which is sigma squared, and it's the square root of this formula. All these formulas are on your formula sheet. They are also on your calculator. So let's go for it. So this example says, consider the discrete random variable x given in the table below. Calculate the mean, variance, and standard deviation of x. Also calculate the expected value, rounded 3 decimal places if needed. So it tells us our x options, 2, 4, 8, 12, 15, and 16, and our different probabilities. So for landing on 2, let's say, our probability is 0.5. For getting a 4, our probability is 0.1. For x equaling 8, our probability is 0.1. For x equaling 12, our probability is 0.13. For x equaling 15, our probability is 0.08. And last but not least, for x equaling 16, our probability is 0.09. So our mean, let's be honest, we're all going to use our calculator. Let's just do our calculator. All right, in our calculator, I'm going to show you how to do it, and then I want to write little notes so that way you go back. You have the recording if you need to go back and watch the recording to see how we did it on our calculator, or you kind of have some notes that you can go back and refer to. I know my battery is low. To remind me that my life is not together. All right, so we're going to go to statistics. We're going to go to stat. Our stat is right here under delete. We are going to edit because we have our new list to put in. Press enter. And then we're going to type x into L1, and we're going to type our probabilities, P of x, into L2. And I want to make sure to label this because sometimes I forget. So this is going to be L1, and this is going to be L2. If you want to clear it out, you could just type over it, you know, and it'll work. But if you want to clear it out, go up to L1, press clear. Notice whenever you press clear, all the numbers clear from down here. And then whenever you press enter, it'll go away. So again, using my arrows to scroll up and hover over L2. Down here will give me my whole list of L2. I want to delete this. So I'm going to press clear and then press enter, and it'll delete it. So I'm starting from scratch. All right, so typing in x into L1. So for L1, I have 2, enter, 4, enter, 8, enter, 12, enter, 15, enter, and 16, enter. So I'm entering all those in. Same thing for L2, putting in my P of x, putting in my probabilities. So 0.5, enter, 0.1, 0.1, 0.13, 0.08, and 0.09. So typing in all those probabilities and x values. So I told my calculator the data. So now we're going to go back to our stat menu. Now we want it to do something with our data. So we're going to go over to calculate. I'll try to give everyone a minute because I know I type it in fast. It's not typed in already. So going back to our stat menu. Just pressing stat. Scrolling over with my arrows to go over to calculate. We have one variable. Our variable is x. I have two columns. So I have x and I have the probability of that x, but it's still just one variable. It's still just x. So we're going to go to one variable stats. Just like we did in chapter 3. Press enter. So for our list is going to be L1, and our frequency list is going to be L2. So I'm going to go down to calculate and press enter. Notice that if you have an 84 plus like mine, or 84 in general, it'll automatically fill this out nicely for you. All you have to do is press calculate. If you have an older calculator, it'll still do it. You just need to tell it what to do. So yours will look like one variable stats. You need to type in L1, comma, L2 to tell it the list and the frequency. So again, if you notice that L1 is above number 1, so second number 1, here's your comma, and then second number 2. And if you press calculate, notice for a split second it says the same thing. And then here's all of our answers. So this page should look the same for everyone. So our X bar is the same thing as our mean, which is 6.4. I'll put a little note X bar in our calculator. X bar is just your mean. Sample mean or population mean, they're found the same way. Going down, our sigma is 5.366563,146, which it said to round to 3 decimal places. So we're going to round 1, 2, 3. We're going to round this 6. Looking next door is a 5. So we get 5.367. Remember, on our calculator, it doesn't give us sigma squared, but that's okay. So if I just want to go out, I can press clear, or I can do second mode, which is our quit button. And I'm going to square this. So in parentheses, 5.366563,146 squared. Remember, I like to write it all out so that way I don't mess up my roundings. And we're left over with 28.8. You would get the same thing that if you did these crazy formulas, but you paid a lot of money for these calculators, so I want you to get your money's worth, and this is a heck of a lot easier than plugging in those crazy formulas. So last but not least, our expected value, which is E of X, which is the same thing as our mean, which is the same thing as mu up here, which is 6.4. And that's it. So we really like these calculators. They were worth every penny because that made that problem a lot better. Questions about calculators or questions in general about this problem before we do this last problem, and then we'll take a break. All right, so it says the Florida Lottery has a game called Pick 4, where a player pays $1 and picks a 4-digit number. If the 4 numbers come up in the order you picked, then you win $3,200. So write the probability distribution for the players winning. So notice it's the winnings. Fill in the table below, enter the left column values from smallest to largest, round to 4 decimal places as needed. All right, so notice it's for your winnings, because whenever I first did this problem, because I do every problem from the homework and from the quiz, from the test, I was thinking that about the pick 4 thing. So it wants our winnings. So X is our different outcomes. And remember, it wants it from least to greatest, from small to largest. Okay, so the 2 outcomes are either you win or you lose, right? So lose or win. If you have to pay $1 to play, if you lose, how much are you out? $1. So -1. You lose $1. So -1. That's your outcome. If you win $3,200, but you paid $1 to play. So how much is your outcome? 31. Yep. $31.99. Yeah. I knew it. That's what you meant, but since you pay $1 to play. And now we need to find the probabilities. So we have to have the 4 digits, right? So we have our first digit times our second digit times our third digit and our fourth digit. So what's the probability of getting that first number right, that first digit right? Well, there's only one right answer. out of how many total? We could pick 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So out of 10 options, so 1 out of 10. Same thing for the second one. There's one right answer out of 10 options total. 10 because you're including 0. Same thing for the third, 1 out of 10. Same thing for the fourth, 1 out of 10. So to find the probability, we're going to multiply all these options together. This is what's called the counting rule that we talked about in chapter 3. This is our counting rule. So we have 1 divided by 10 times 1 divided by 10 times 1 divided by 10 times 1 divided by 10. Notice how they're all in parentheses, so that way each fraction separately. If you wanted to do 1 divided by 10 to the fourth, yes, that's good. I was just trying to stick with the counting rule. And you're left over in your calculator with 1e to the negative fourth, which does not mean that you did it wrong. You're right. This is the same thing as saying 1 times 10 to the negative fourth power. So my decimal at the end has to move over 4 times to the left. So 1, 2, 3, 4. Filling in all those gaps with zeros. So 0.0001.
Where do you get the 10 from? 10 is on that one.
No, it's okay. So this E right here in your calculator is going back to scientific notation.
No, what I mean, like above first digit, second digit.
Oh, sorry. I thought you meant this end. No, it's okay. So it's saying that there's one right digit out of 10 digits total, because it could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10 options. Thank you for asking. Any other questions? So this 0.0001 is your probability of what? Winning or losing? Winning. Yeah, thanks, Sage. Winning. Because there's one right option out of 10 total. So probability of winning. So 0.0001. Now you could do the same thing for losing. There's 9 wrong options out of 10 total. Or we know for our probabilities, they have to add up to 1. So I could just say, okay, 1 minus 0.0001. That's my probability of losing. So 0.9999. That's 4 decimals, so we're good. So 1 minus 0.0001. So that is our probability distribution. All right, so B and C, it says, what are your expected winnings? Round the answer to 2 decimal places since the value is interpreted in dollars. So what is our expected winnings? Expected winnings is your expected value, your E of X, which is your mean, which you can plug into your calculator, but honestly, this one is easier to actually use the formula since it's so little. Since we did the plug it into your calculator, same thing on the last one, let's just plug it into our formula. The sum of X times P of X. So adding up X times P of X, so X is -1 times P of X, which is 0.9999, plus our X, which is 3199, times the probability 0.0001. Again, one more time, just to reiterate, if you want to plug this into list 1, plug this into list 2, like we did earlier, that's fine too. This one's just easier because it's such a small list to do it this way. So either way, totally, you'll get the same answer, totally up to you. So -1 times 0.9999 plus 3199 times 0.0001. And this will give us -0.68. So that is our expected value. That is your expected winnings, which is okay that it's negative. I get people who like freak out that it's negative. That's okay. So what is the interpretation of the expected winnings? So that is our expected value. Expected value means if you play this over and over and over and over and over, that's what you're expected to come out with in the end. So if you play pick 4 many times, you can expect expected value to win negative $0.68 per game. That's just the way they worded it. To me, that sounds weird because you're going to win negative 0.68. You're going to lose 68 cents per game. You're going to lose 68 cents per game. Because it said what are your expected winnings? Your expected winnings are negative 0.68, which means you're going to lose 68 cents every game. So questions, comments, concerns on that part so far? So if not, let's pause right there. And we're halfway through, so that's good. We're going to pause right there, take about a 5-minute break, and then we'll come back, wrap this up, and then we'll be done. Let me pause this. All right, so binomial distributions. So all binomial distributions have the following characteristics. Going back, we talked about distributions before. Now it's just a specific type of distribution. So we're just kind of getting more specific. So there's a fixed number of trials, and it's denoted by n. Because bi means 2, so there's only 2 possible outcomes per trial, and we call it either success or a failure, whatever the situation might be. Again, let P denote the probability of success, and then this time Q is going to be the opposite, so Q is the probability of failure. That's just what they use, P and Q. Trials are independent. That means that the occurrence of one does not affect the other. So the trials of P and Q don't change from trial to trial, so it always stays the same. So for a binomial distribution, the random variable x represents the number of successes out of n total trials. Whenever we say success, the term success doesn't mean good or bad. It's just like what we're looking for, and the problem will tell you what you're looking for. So success means you're getting what you're looking for. So we have formulas for our mean, which is our expected value. Notice these formulas are easy because it's just n times p. So our mean, which is mu, which is our expected value, is just n times p. N is the number of trials times p, which is the probability of success. Our standard deviation, which is sigma, is the square root of n times p times q. N is the number of trials, p is the probability of success, q is probability of failure. Probability mass function, which is PMF, is a function that generates probabilities when specific outcomes are input. So probabilities for binomial variables, so probabilities for PMF, is the formula to find the probability for each variable in a binomial distribution, and we have our little formula here. So P of x equals n combination, going back to our combinations from chapter 3, x, p to the x power times q to the n minus x power. Remember, n is the number of trials, p is the probability of success, q is the probability of failure. By the way, q, probability of failure, if you either succeed or fail, that means that whatever's going to be left over. So in order to find the probability of failure, in order to find q, it's always 1 minus p. X is the number of successes, and then the number of failures is whatever's left over, so n minus x. Let's do an example. So suppose you have an experiment where you toss a fair coin 3 times, so a regular coin 3 times. You then count the number of heads observed over 3 tosses. Use this experiment to address each of the following questions, round to 3 decimal places. So first it says define the random variable. Okay, so before I start the problem, let's make a note. What happened to my pencil? I know this is a binomial distribution. I know this is a binomial distribution once it's under binomial distribution in the notes, but more so because there's 2 outcomes. You toss a coin and it's either heads or tails. It told me 3 times, so I'm gonna have 3 trials, so n equals 3. And then again, we have 2 outcomes for each trial, and it's going to be heads or tails. Heads or tails. So actually starting the problem, again, just like we did before, I like to write out everything that they give us. So that's everything that they give us. So defining the random variable, x is our random variable, so x equals. It tells us in here we're looking for heads. So x is the number of heads observed when you flip a coin 3 times. Number of heads observed when you flip a coin 3 times. So construct the probability distribution table for the number of heads obtained over 3 tosses. Enter the x values from smallest to largest. So if you toss a coin 3 times, how many number of heads can you observe? So if all 3 of them are tails, going from least to greatest, you could have 0 heads. You could have 1. You could have 2, or you could have 3. You can't have more than 3 because you only toss the coin 3 times. So if none of them land on heads, if one of them land on heads, if 2 of them, or if all 3 land on heads. Those are different outcomes. So we need to find our probability. So instead of using our formula like we did before, let's just go straight to our calculator. All right, so let's use our calculator. All right, so notice I want a distribution. So notice above vars says this distribution. So I'm gonna hit my second button and then the vars button. So here's my second, here's my vars. That will give me my distributions. That will give me distribution. Remember, this is a binomial distribution, so that's why I'm going to distributions. So it's a binomial distribution. So if I scroll down, notice letter A says binom PDF. Binomial distribution, probability, so probability of a binomial distribution. So binom PDF. If I press enter, on an 84, it'll like tell me straight up what do I need to know. If you have an older calculator, you're just going to put it in an order. So the number of trials, which is our n, which in this case is 3. Our probability, which is p, which in this case, our probability of landing on heads, it's either going to be heads or tails, so 0.5. And then our x value. So for this first one, our x is 0. So if you have an older calculator, you just have to put it in manually. So n, which is 3, our probability is 0.5, and then x is 0. Going down to paste, notice it says the same thing. So if you have an older calculator or a newer calculator, our calculators should all look the same. And then press enter. So it gives me 0.125. Now that was when x is 0. So 0.125. So we're going to do the same exact thing when x is 1, same thing when x is 2, same thing when x is 3. So a couple different options. If you want to just type it all out the same, that's fine. Or if you press second enter, it'll give you your entry from above. So second enter, and then you can just scroll, change that 0 to a 1. So you're going to do binom PDF, 3, 0.5, 1, and then press enter. Will give you 0.375. Same thing when x is 2. So binom PDF, 3, 0.5 when x is 2. Then we're going to press enter. Remember in your calculator, you can, to save you from having to type this whole thing over again, press second, enter. I'll write that as in a little note in a second. And that will give you your previous line. So second enter will give you your previous line. Then I can use my arrows to scroll over and change that 1 to a 2, which is also 0.375. And then last but not least, binom PDF. 3 is our n value, 0.5 is our probability, and our x value is 3. Then press enter. And that will give me 0.125. So note, you press second and then enter. It will give you what you previously entered. Just to kind of save you some time. You press second and then enter. It will give you what you previously entered. So that's our calculator. I want to show you one other way. So you can do the formula, which no one's going to do, so I'm not going to waste your time. The calculator or a table. And I'm going to show you that next. I want to give you a second. Questions on the calculator part? Questions on the calculator part? So you do each one separately when x is 0, 1, 2, and 3. Yes, ma'am. Thank you. I seen your face, so thank you. The 0.5? Yeah. All right, so if I flipped a coin and it lands on heads, my probability is going to be 0.5. It's like 1 out of 2 options. So probability. So there's going to be 1 head out of 2 options total, out of heads and tails. So 1 out of 2 is 0.5. Thank you for asking. And then remember, n is the number of trials. Oh, I meant to do that. Oh yeah, no, n is number of trials, so 3 trials. So we did this 3 times. Any other questions? All right, so if you notice at the back of this packet, you have your formula sheet. This is the same formula sheet that you're going to get on the test. Here's our formulas. And then we have all the numbers. This is what's called our binomial distribution table. This is what's known as our binomial distribution table. Yeah, so I'm gonna give you this too. So it'll give you like this whole packet. So I'll give you from page 9 on. So the tables, and you'll get the formula sheet on the test. This is how you did it before we had calculators. So this is totally another option, and it's kind of personal preference. Sometimes I do problems this way, sometimes I do it with a calculator. It's totally up to you. So this is what's called a table of binomial probabilities. So it pretty much just does all the work for you. So for this one, we know we have 3 trials, and we know that our probability is 0.5. So 3 and 0.5, this will tell us when x is 0, here's our probability. When x is 1, here's our probability. When x is 2, and when x is 3. Notice it's the same thing that we got on our table. It just does it all for you. So instead of entering it all in, you could just do it this way. So again, our probability was 0.5. Our n value is 3. When x is 0, my probability is 0.125. When x is 1, my probability is 0.375. When x is 2, my probability is 0.375. And when x is 3, my probability is 0.125. So it just says it for you. So you can either do it on the calculator or on the table, totally personal preference. You have the table on the test and you have the calculator on test. Questions on this one? So I'm just going to write a little note going back to our page. So you can also do it on the table. And then in which our probability was 0.5, our n value was 3. And then we looked whenever x was 0, 1, 2, and 3. Sorry. So totally up to you, calculator or table. This one, the table was kind of easy. Whatever one you like better, whatever floats your boat. I have one more question, part C, for this problem on the next page. And it says, oh no, sorry, 2 parts, or no, there's a lot of parts. I don't know what I'm looking at. My bad. But while you're still copying this, it says determine the shape of the probability of x. So looking at this, and remember it's going to be a drop-down menu, so you have options to choose from. But I see that it's symmetric, meaning that 0.125 are on my outside and 0.375 is in the middle. It's symmetric. So that's going to be my shape. So the shape of x is symmetric. It's not random. It's not skewed left or right. There's not a hump and then a tail. It's symmetric. Next, it says find the mean number of heads for the distribution. So our mean, which is our mu, going back to our formula sheet, or going to our formula sheet, I should say, it tells us mean and standard deviation for binomial distributions. So n times p. This is an easy formula, so we're just going to use this one. So n times p. So n we know is our number of trials, which is 3, times p, which is our probability, which is 0.5. So 3 times 0.5, which will give us 1.5. Done. That kind of looks weird. But 3 times 0.5, n times p. The mean of the discrete probability is also denoted as our e of x, which is our expected value. So again, what is the interpretation of this mean? Now let's throw this in there. And again, it's going to be, let's see, multiple choice on the test, drop-down menu on the homework. So what is the interpretation of the mean? So if you do this over and over again, so this experiment was flipping the coin. So if you flip a coin 3 times over and over again, because that was our experiment, flipping it 3 times. You flip a coin 3 times over and over again. You can expect to get an average. Mean is an average of 1.5 heads for every 3 flips. Again, expected value means if you do the experiment over and over and over again, that's going to be your average. So if you flip a coin 3 times over and over again, that's going to be your average. That's going to be about the number of heads you're going to get for each experiment, for each 3 flips. Last, no, it's still not last, part E. Find the standard deviation for the number of heads. So going back to our formula sheet, the standard deviation is the square root times n times p times q. Standard deviation is the square root of n times p times q. It's on your formula sheet. Remember that Q is 1 minus P. So the square root of N, which is the number of trials, which is 3. P, which is our probability, which is 0.5. And then Q, which is 1 minus P, so 1 minus 0.5 is still going to be 0.5. So the square root of 3 times 0.5 times 0.5. And that will give us our standard deviation, which is 0.866. It told us in the problem to round 3 decimal places in the original problem. Finally, here's the last one. So find the probability of obtaining 1 or less heads over the 3 tosses of a coin. So 1 or less. So that means our probability of x being 0 plus the probability of x being 1. So 1 or less. I'm going to use this table so it goes back. Whenever x was 0, our probability is 0.125. Plus our probability when x is 1 is 0.375. So adding those two together, and we get 0.5. Done. Done. So that's that whole problem. Questions, comments, concerns on that one before we go to the next example? Just kind of like putting it all together. So it says, let x be a random variable that possesses a binomial distribution with p being 0.8 and n being 10. Use the binomial formula or the tables and calculate the following probabilities. Also calculate the mean and standard deviation. Round up 4 decimal places as needed. So it's the same concept. It's just a little bit more straightforward. It tells you that p is 0.8, n is 10. And it's saying, what's the probability that x is greater than or equal to 8? So that means the probability when x is 8 plus the probability when x is 9 plus the probability when x is 10. And we know they have 10 trials, so I know nothing's more than 10. So we can either use our table or we can use our calculator. Either way, if you use the calculator, it'll look like binom PDF. N, which is our number of trials, which is 10. P, which is our probability, which they told us is 0.8. Oops. And x is 8. Plus binom PDF. 10 is our number of trials. 0.8 is our p-value. X is 9. Plus binom PDF. 10 is the number of trials. 0.8 is my p-value. 10 is my x value. Remember, it's n times p, or n comma p comma x. So in my calculator, math, nope, second bars, going down to binom PDF. 10 trials, 0.8 is my p-value, my x value is 8. Pressing paste. I can say plus second bars, binom PDF. 10 trials, p-value still 0.8 when x is 9. Plus second bars, binom PDF. 10 trials, p-value is 0.8 when x is 10. So all I have to do is change that. And I added them all up together. And then boom, there's my answer, 0.6778. So it says round to 4 decimal places. So rounding this 7, looking next door is a 9. So that would give us 0.6778. I'm going to not write that down because I want to show you if you do it on the table. So pulling up our table, I'm going to use this one. It's the same thing. It just looks, it's not stapled. Our p-value is 0.8, so I know I'm going to be looking at this column. P-value is 0.8, so I know I'm going to be looking at this column. Our n value is going to be 10. Forget it. So looking when our n value is 10, our p-value being 0.8, and then going here where these match, we're going to go down when x is 8, 9, 10. So we're going to add up those 8, 9, and 10. 8, 9, and 10. So 0.3020 plus 0.2684 plus 0.1074. And notice you get the same thing. So whatever floats your boat, go for it. So again, our p-value is 0.8, so I'm looking at this column. My n value was 10, and then looking now when x was 8, 9, and 10. So these three values right here. Either way, you get the same answer. So going back to the problem. Just to write it down so you can do on our calculator or on the table, we had 0.3020 plus 0.2684 plus 0.1074. So you can do it on the calculator or the table. Either way, you get the same answer, which was 0.6778. All right, so same thing for the next one. What's the probability when x is less than or equal to 5? So that means the probability when x is 0, plus the probability when x is 1, plus the probability when x is 2, plus the probability when x is 3, plus the probability when x is 4. It says or equals to 5, so including 5, plus the probability when x is 5. So we can do the same way in our calculator. So binom PDF. 10 is our n value, 0.8 is our p value when x is 0, plus when x is 1, binom PDF. 10, 0.8 when x is 1, plus binom PDF. 10, 0.8 when x is 2, plus binom PDF. 10, 0.8 when x is 3, plus binom PDF. 10, 0.8 when x is 4, plus binom PDF. 10, 0.8 when x is 5. So not hard, just tedious. So second vars, binom PDF. 10.8, this time my x is 0, plus second vars, binom PDF when x is 1, plus second vars, binom PDF when x is 2, plus second vars, binom PDF when x is 3, plus second vars, binom PDF when x is 4, Almost done. Second vars, binom, PDF, when x is 5. And pressing enter, that will give you your answer at 0.03279, which will round up to 0.0328. All right, so that's one option, the calculator. That I feel like is the easiest option. That's the first time I've done it in your calculator. You have another option in your calculator, but people get super confused. So if you get super confused, just do it the same way every time. Just do it like this. But I want to show you, if you want a shortcut, there is a shortcut. So I don't want to like not tell you the shortcut. There is a shortcut, but people get confused on it. So I wanted to give you both options. So another option as a shortcut in your calculator is if you go to second vars and you scroll down, it'll also say binom CDF. That CDF means it's cumulative. So just like we talked about cumulative frequency, or we talked about a cumulative final exam, that means that you're going to take a final exam on this stuff and everything that you learned before it. So that's what the cumulative means here. That means it's going to be 5 and everything before it. So in your calculator, you can do binom CDF, 10 trials, p-value 0.8. and our x value is 5. That will do this whole long thing in one shot. It just has like this formula plugged in. It'll say when x is 5, 4, 3, 2, 1, 0. 5 and everything before it. Pressing paste, boom, same answer. So people just get really confused on when do you use CDF, when do you use PDF. So I was just trying to make sure if you want the shortcut, use CDF. Another option is our PDF, which just gives you each of them. So if you get confused, I think it's easier to just use PDF for everything. So those are both your options. I want to give this option to your calculator. And then shortcut on calculator is binom CDF. Our n values still 10, p values still 0.8, and then our x values 5. So this will add the probabilities when x equals 5 and everything before it. So CDF will give you the cumulative, which means it'll give you 5, and add everything before it. Yes, ma'am.
So say, for example, that problem said the probability of x less than 5 instead of less than or equal to, would you just put 4 then in its place?
Yeah, no, great question. Yes, you're right. So if it said less than 5, that doesn't include 5. So that means you'd have to do 4 and everything before it. So you'd put in 4 for x. Great question. If it's something like where it's the opposite, if it said x is greater than or equal to 5, it doesn't do the opposite. So, because I feel like I should tell you. So if the opposite of this would be 1 minus. So you could do 1 minus like up here. You could do using the shortcut. It's the opposite sign, so you could do the opposite. Opposite means 1 minus binom CDF when n is 10. I really wanted to make sure I had enough. Let me switch this over. Comma 0.8 comma, and then you'd put in 7 because it wants 8 to be in here, and then this would be adding up 7 plus 6 plus 5, 4, 3, 2, 1, 0. So it's saying, okay, this will take out all this stuff, and it wants whatever is left over, so you can do 1 minus. If you don't like the shortcuts, again, don't do the shortcuts because people, like I said, get confused which time to use when. But if you like the shortcuts and you get it, you do you. So thank you for bringing that up because I kind of mentions that point. And then your third option is the table. So going to the table. We're still looking at this column when our p-value is 0.8. We're still looking when n is 10, and then we're going to add up whenever x is 0, 1, 2, 3, 4, 5. So here's what we're adding up. So 0 plus 0 plus 0.0001 plus 0.0008 plus 0.0055 plus 0.0264. So just adding up all of those probabilities that we circled. And it gives you the same thing, 0.0328. So if you like the table, if you like the calculator, you do you. So on the table, we have 0 plus 0 plus 0.0001 plus 0.0008 plus 0.0055 plus 0.0264. Either way, it'll all give you the same, which is 0.0328. So that was all for that first problem. After doing all that, these are my favorite. We just have one, when x is 9. So calculator or table, same concept. So we're just looking at the probability when x equals 9. So in our calculator, let me do the arrow since I've been doing the arrow. So binom PDF. 10 is my n value, 0.8, and when x is 9. So second bars, I have binom PDF. PDF just does one at a time, so 10.8, and when x is 9, boom, there's my answer, 0. What happened? There you go. 0.2684. Or you can also look at your table. Going back to our same place we've been looking when our p-value is 0.8, n is 10, and x is 9, we get 0.2684. Same thing. If I have the table, I like to use the table because it's a little bit more tangible, but I don't always have a table with me, so your calculator is kind of another option. So either way, 0.2684. All right, so next I have our mean. Mean is n times p. N we know is 10 times p, which is 0.8. So 10 times 0.8 will give us 8. And our standard deviation, which is the square root of n times p times q. It's on your formula sheet, but you just get so used to it. Remember, q is 1 minus p. So 1 minus 0.8, which would give us 0.2. So I have the square root of n, which is 10, times p, which is 0.8, times q, which is 0.2. Who has hiccups? Square root of 10 times 0.8 times 0.2. And that will give us our standard deviation. which is 1.2649. Done. So really one more page. That last page is super easy. So one more page, a real page. I'll say 1.5. How about that? And then we're done. Questions on this, whether it's a calculator, whether it's a shortcut, whether it's a table. I just wanted to give you different options. And you kind of, as you do your homework, you can figure out what options you like best, and then you kind of stick with that. So questions, comments, concerns. That's what's hard for me, because some people, it's totally personal preference. So it's not like one way is easier than the other. It's literally personal preference. So whatever way you like better, I don't want to do one and then you like the other one better. So I try to give you all options. Ready for the next page? So it says a large fast food restaurant is having a promotional game where the game pieces can be found on various products. Customers can win food or cash prizes. According to the company, the probability of winning a prize, large or small, with any eligible purchase is 0.116. Consider your next 34 purchases that produce a game piece. Calculate the following. This is a binomial distribution, rounding your answer to 4 decimal places. Okay, so let's see what it gives us. It tells us that the probability is 0.116. So it tells us that P is 0.116. So look at your next 34 purchases. So it tells us that N is 34. So looking at N is 34, just starting off there. If you notice, your table only goes to when N is 25. So because it only goes to 25, that's not going to be on my table. So you have to use your calculator for this problem. So not on the table. So must use your calculator. So your calculator can do all of them. Also, that p-value is not on our table either. So the first question says, what's the probability that you win 4 prizes? So that x equals 4. So what's the probability that x equals 4? 4 prizes. So we have binom PDF in our calculator, like we did on the previous problem. Our n value is 34. Our p value is 0.116, and x is 4. Remember, it's n, comma p, comma x. If you have a newer calculator, you don't ask you for it, but if you have an older calculator, you have to put it in manually. So second bars going down to binom PDF. 34 trials, p is 0.116, and x value is 4. So all of our calculators should look the same. Boom, there's our answer, 0.2078. $0.2078. All right, so what's the probability that you win more than 7 prizes? So what's the probability that x is greater than 7, more than 7? So more than 7 means that it's going to be 8 through 34. Well, I don't know about you, but I don't want to do when x is 8, when x is 9, x is 10, all the way to 34. That's a lot. So here's where we can use our shortcut. We know this is the same thing as saying 1 minus the probability of x being greater than or equal to 7. Remember, 1 minus means opposite. So our opposite sign of greater than 7 is greater than or equal to 7. I'm sorry, greater than, and this is less than or equal to 7. So the reason why I wanted to change it to less than or equals to is because I can use that cumulative shortcut. That means it'll be 7 and everything below it. 7, 6, 5, 4, 3, 2, 1, 0. And then the 1 minus will give me whatever's left over. So that will give me the 8 through 34. So in my calculator, we can do 1 minus binom CDF. Our n value is 34. Our p value is 0.116, and our x value is 7. Remember, it's n, p, x. So because it's CDF, this will give you when x is 0 all the way through 7. So it'll add up all of that for you. Then the 1 minus will give you whatever's left over. The leftovers were that 8 through 34 that we're looking for. So in my calculator, 1 minus second bars going down to binom CDF, 34 trials, p is 0.116, and our x value is 7. Boom, there's our answer. So 0.0374. Way better, which you could still do it if you want to do it. If you want to do 8 plus 9 plus 10 plus 11 all the way to 34 with the binoms PDFs. But this just saves you a lot of time. So maybe just to kind of like put it into a notes thing up here. So we're going to use binom CDF. Whenever it's x is less than or equal to some number. So it can be that number and less. And then we're going to use binom PDF when just x equals some number. So PDF is just for 1 point. So you can think of P as in point, and C, which is cumulative, which is that number and everything less. All right, so the next one says, what is the probability that you win between 2 and 5 inclusive prizes? So including 2, including 5. The probability that x is between 2 and 5, including 2 and including 5. So that means the probability that 2 is less than or equal to x is less than or equal to 5. So here, we could just kind of go old school. So binom PDF or here, let me say this. Probability when x is 2 plus probability when x is 3 plus probability when x is 4 plus the probability when x is 5. So we're going to do second bars, binomial PDF. Oops, wrong button. We said we had 34 trials, P is 0.116 when x is 2. Paste. Plus second bars, binomial PDF. Everything stays the same, 34 trials, P is 0.116 when x is 3. Paste. Plus second bars when x is 4. Binomial PDF when x is 4. Paste. Plus second bars, binomial PDF when x is 5. Equals, there's your answer. 0.7218. 0.7218. So for this one we did binom PDF 34, 0.116, 2, and then changed all the way to 5 and added. Last one, what's the probability that you win one or fewer prizes? So probability that X is less than or equal to 1, so 1 or less. So 1 or less, that means we can use our CDF. So probability or binom CDF. 34 trials, P is 0.116, and our X value is 1. Second bars, binom CDF. It's 1 or less. 34 trials, P is 0.116, and our X value is 1. There's our answer, 0.0825. So one more like real problem, and then on the last page, will take us 2 seconds. Before we go, these two are a lot. So questions on this one? Questions on this one? So it's the same thing we've been doing, just kind of putting it all together. Let's do one more. So it says in a recent survey found that 50% of all, I'm making up words here. A recent survey found that 50% of IRSC students plan to go on vacation after graduation. So by the way, that's telling us our probability. So 50% is our probability. Suppose that 5 IRSC students are randomly selected, and let X be the number of students that plan to go on vacation after graduation out of the sample of 5. So use the binomial probability formula or binomial probability table to construct the distribution of X. Also use the binomial probability formula table to construct the cumulative probability distribution of X. All right, so our N value, we're talking about a sample of 5, so N is 5. Our probability, they told us, was 50%, which is 0.50 or 0.5. So because N is 5 and P is 0.5, that's on my table. So N is 5, P is 0.5, that's on my table. So I'm able to use my table or the calculator this time. I have the option. So we can use table or calculator. Can use the table or the calculator. So they tell us when X is 0, 1, 2, 3, 4, 5. It's binomial because it's either they are going on vacation or not. So yes or no. So if you want to do it in your calculator, it would be binom PDF. Our N value is 5, our P value is 0.5, and then you're going to plug in your different X. When X is 0, when X is 1, 2, 3, 4, 5. So as you're copying it down, just to show you in your calculator, second bar is binomial PDF. 5 trials, P is 0.5 when X is 0. Second enter when X is 1. Second enter when X is 2. Second enter when X is 3. Second enter when X is 4. Second enter when X is 5. So these are all the numbers that are going to go on my table. These are all the numbers that are going to go on my table right here. Or you can use your table. So your table says when P is 0.5, When n is 5, here's my table. When x is 0, 1, 2, 3, 4, 5. Boom, that's my table. 0.0312, 0.1562, 0.3125, 0.3125, 0.1562, and 0.0312. If you notice, like, I think on my calculator, this one is 0.03125. So it'll just round up. The homework is programmed to know either one, so it should accept either one. So either one you put on there is fine. On the test, it'll be multiple choice, so you could see that it's 2. So it's not going to give you 2 or 3 as it'll pick on you. All right, so when x is 0, we had 0.0313, say, or let's say 2. When x was 1, it was 0.1562. When x is 2 for my table, 0.3125. When x is 3 from my table, it was again 0.3125. When x is 4 from my table, 0.1562. And when x is 5, 0.0312. Just copying it down. I copied from my table, or you can copy from your calculator. Either way. When x is 0, 1, here's 2, 3, 4, and 5. So next, this says the probability when less than or equal to x. So this is going to be cumulative. This is going to be your cumulative probability. It tells you that here, cumulative. Which means it's going to be x or less. So when x is 0, there's nothing less than that, so it's just when x is 0. When x is 1, that means it's going to be the probability when x is 0, plus the probability when x is 1. When x is 2, it's going to be the probability when x is 0, plus the probability when x is 1, plus the probability when x is 2. 3 would be the probability when x is 0, plus probability when x is 1, plus the probability when x is 2, plus the probability when x is 3. So let me just start. So when x is 0, we get 0.0312. So when x is 1, we have that 0.0312 plus 1, 0.1562, which would give us 0.1874. So it's going to take that 0.1874 plus when x is 2, so plus 0.3125. Remember, this is when x is 0, 1, and 2. So 0.4999 plus when x is 3, so 0.3125. Oh, shoot. Plus, 0.3125. So 0.8124. So now instead of writing 0, 1, 2, 3, I can just say, okay, it's that 0.8124 plus when x is 4, so plus 0.1562, which would give us 0.9686. So taking that 0.9686 plus when x is 5, 0.0312. Oh, I put 2 pluses. I get 0.9998, which is about 1, because we added a little bit of rounding, which we know it should be about 1. That squiggly equal sign means about. Which we know it should be about 1, because if it gives us everything, everything's about 1. So just like we had cumulative frequency distributions on test 1, same thing, we're just doing probabilities now. Questions on how we got the table? Okay, so our 2 questions based off this table. Calculate the probability that no more than 2 students out of the random sample of 5 plan to go on vacation after graduation. So it tells us the probability that x is less than or equal to 2. So the probability of x being 0 plus the probability when x being 1 plus the probability when x being 2. We already did this right here. And we got 0.4999. Remember, if you use the calculator instead of your table, you're going to get a little bit different, but it'll still take both of them. It'll give you 0.5 instead. Same thing for the last one. It says calculate the probability that 2 or more students out of the random that more than 2 students out of the random sample of 5 plan to go on vacation after graduation. So probability that x is greater than 2. So that means the probability that x is 3 plus the probability that x is 4 plus the probability that x is 5. So 0.3125 from x is 3 plus 0.1562 when x is 4 plus 0.312 when x is 5, and that would give us 0.4999. By the way, notice that these are opposites. So 1 is less than or equal to, 1 is greater than. So, or you can do the opposite. So 1 minus the probability that x is less than or equal to 2, which is 1 minus 0.4999, which would give you 0.5001. So either one of these 2 answers would be marked correct. 2 different ways of doing the same problem. So whatever way you like better, you do you. One more little tiny thing on the next page and we are done. Before we go to that little tiny thing on the next page, questions, comments, concerns, how can I help you with this stuff? And I'm recording, so if you need to go back and remember what we did, we have that option too. I'm trying to put it all on one page. All right, so this last thing is the shape of the binomial distribution, and it's just rules. It says if our probability equals 0.5, then we know it's going to be symmetric. If our probability is greater than 0.5, then we know it's going to be skewed to the left. And if the probability is less than 0.5, we know then the binomial probability distribution will be skewed to the right. Just rules. So determine the shape of the graph of the following binomial probability distributions. Let x be the binomial variable with p being 0.5 and n being 322. Then the probability distribution of this data will be blank. So it tells us p equals 0.5. So we know from up here when p is 0.5, we know it's symmetric. Done. That's it. I don't care what n is. I'm just looking at p. Same thing for the next one. Let x be the binomial variable with p being 0.57, n being 157. I don't really care. Then the probability distribution of this data will be blank. So looking at our p-value, 0.57. This p-value is greater than 0.5. Greater than 0.5 means skewed to the left. Last but not least, let x be the binomial variable with p being 0.22. This p-value is less than 0.5, so we know from our rule, less than means skew to the right. And that is all of chapter 4. Wasn't too bad besides those last 2 examples. So don't, I feel like we ended on a, well, this stuff was good, but don't think about those last 2 examples. It'll just all come together. So use the chapter 3 homework should be done. Use this to help you do chapter 4 homework, and then make sure that you study and bring it all together by doing the test 2 extra credit. So next class will be the test where the homework, the quizzes, and the extra credit will be due. If you have any questions, please let me know. Let Delaney know, let the ASE lab know. If not, have a great week. Thank you very much. I will see you next week for the test.